directly building a model like we did in simple linear regression. Then secondly, I'll tell you how to split the data and then create a model. First, what we are taking in independent variables are horsepower and weight. So I am plotting the data. I am plotting MPG with respect to horsepower. So to plot the graph, the command is plot. Within the bracket, first is the dependent variable in reference to the independent variable, comma, the name of the data set. Let's execute this command. And what we can see is, as horsepower is increasing, MPG is going down. So there is a negative relationship. Next is weight. It is the same relationship. When weight increases, MPG goes down. Now I am building a model. I am saving the values in a variable called result. It is the same way we created simple linear model. The formula is same, LM. Within the bracket, it is the dependent variable, that is MPG, the variable we want to predict in relation to horsepower plus means we are adding one more factor for predicting the value of MPG. So we are taking horsepower and weight, comma, the name of the data set. Let's execute this command and let's check the summary of this model. Now what we can see is both horsepower and weight is significant as their value is less than 0.05, that is p value, and also we have 2 stars and 3 stars with the factors. Now how do we get that these factors should be taken or not? We can also see there is r squared values. Whenever we are taking multiple linear regression, what we should always prefer adjusted r square. And one more factor is there, that is what r square does is it always increases whenever the variables are increasing. It should increase. It shows that our model is significant and giving a significant outcome. What adjusted r square does is adjusted r square adjusts the number of factors considered while predicting the value. So the value should increase, and adjusted r square always adjusts the number of variables and gives a significant outcome. Next, we can see p value is also less than 0.05, which means the model is significant. Now what we will do is we'll checking the multiple collinearity. First, we'll be splitting the data. So what is the use of splitting the data? We are dealing with very small data here, but data can be very large. So it is very helpful to build a data and test the data from same data set. When we divide the data into training and test data set, what we will do is we'll build our model on training data set and we'll test the value of outcome with test data set. So how to split the data? The command to split the data is what I am saving this split indices into training row index. So I am taking the command sample. So sample command will split the data as we have taken the probability as 0.8. So it will take the 80% of the data. How will it split is, first I am giving how many rows are there. So 1 to n row of empty cars. So n row means the last row of the empty car till there. What I want is I want 80% of the data. I am taking the 80% of the data into this variable and it will take it randomly as I am taking the sample command. Out of those 32 rows, it will randomly take 80% of the data and it will transfer it to the variable training row index. After that, I am creating a variable training data. Now out of those empty car data set, the 80% of the data will be transferred to training data set. I have taken the square bracket, which means empty car square bracket, that is I am subsetting the data based on the training row index, that is 80% of the total data I want in training data set. Comma means all the columns but only 80% of the rows. Then remaining into test data. Test data, the variable name, and I am giving the name of the data set, that is empty cars. Again square brackets, I am subsetting the data minus training row index. What does it mean is all the remaining rows which were not taken in the training data should be taken in test data. Let's execute this command also. Now let's create the model. Now I'm building the model on training data set, and we'll be testing the data and testing the model with the training data test data set. So we'll be building the model on training data set and testing our model with the test data set. To build the model, I am taking four variables, that is cylinder, displacement, horsepower and weight. So let's build this model and let's check the summary of this model. So what you can see here is, let's check the coefficients first. It will help us to know whether the factors are significant for our model or not. So as you can see, there are 3 stars with weight, which means weight is a very significant factor in order to predict the value of MPG, but remaining cylinder, displacement and horsepower are with very less stars, very less significance scored, which means they are less significant. Now how do we understand which factor to remove first? So we'll be removing them one by one based upon their p-values. So what we know is p-value should be less than 0.05. Now you can see there are two factors which a little bit significant, but you can see displacement is not at all significant in order to predict the value of MPG. So what I am doing is I am removing displacement from my model first. To remove the factor, what you can do is just comment that factors using a hash key. Now again execute the command. This time it will only take cylinder, horsepower and weight, and let's check the summary again. Also in the earlier model which we created with displacement, you can see the multiple r square and r adjusted r square is 0.8408, around 84% or 86% accuracy is there. What it tells is 86% of the data is helping us to predict the value of MPG. Now what we want is this value should either increase or it should give a positive result in order to get a significant model and better predictions. So our next model that we created is with cylinder, horsepower, weight, and we are predicting the value of MPG. Let's check its summary. So now the other factors, that is cylinder and horsepower, they have there is no stars here, but one of the factors should be significant enough in order to predict the values. You can see our r squared value has improved, has gone down. So what you can see is we have removed displacement from our model and the value of the factors has changed. There are the p-value of cylinders and horsepower has increased, but we will be removing the cylinder first because it is higher in the p-value. So let's remove the value of p-value related to cylinder. Execute the model again. Now what you can see is both horsepower and weight has become significant for the prediction of MPG value. Both values have p-value less than 0.05 and r squared of the model has also improved. So what it is saying is 83% of our model, data of our model helps to predict the value of MPG, and the p-value of model is very less. It is very less than 0.05, which shows now the model is significant to predict the values. Now how do we check if our data, if our model is giving good result, they are predicting correct values? So we will be testing it with the help of test data. I am saving the values in the variable test data $mpg_pred. What it means is in test data variable I am adding a column that is mpg_pred, and I am saving the values of predicted values from the model. Now let's execute this command. Within the predict function I am giving the model name, and after that the test data that we created earlier. You can see what I have done is I have only executed test data here. So it has given me the values that are present in variable test data, and I will be adding a column here with the name mpg_pred, within which the value of prediction will be saved. Now let's execute this command. and check the table. Now you can see what we have done is there is MPG column here and there is predicted value of MPG. The actual value that the data set was having is 21.4 for Hornet 4 drive. That is the name of the car. And my prediction for this MPG is 21.19, which is more or less very near to it. Similarly, you can see there are two deviations, but otherwise the data is matching very nicely. So we can see our model is predicting correct values. Now, how to check if our model is accurate or not? How much there is deviation in our data? For that, there is MAPE calculation. MAPE, it means mean absolute percentage error. So we will be calculating the mean value of the errors that occurred during the prediction of values. For that, formula is we will be taking mean. So the formula is mean. Within the bracket, I am taking the absolute values. For that, the function is ABS. It tells you that the values whichever will be resulting, it will be in absolute form. So I am subtracting the actual MPG values from the predicted values of MPG, dividing it by the original values, and I will be taking the mean of this whole formula. Let's execute this command and let's check the value of MAPE. So you can see MAPE is 0.14, which means there is 0.14 deviation in the values of predicted values. The lesser the value of MAPE, the better it is. It shows there will be less error in the prediction of our predicting variable. Now, how to check the assumptions, whether the model is meeting our assumptions or not? We will be plotting diagnostic plots. The formula I have already we have discussed in simple linear regression also. It is plot within the bracket name of the model. So let's check the first graph. It is the residual plot. So you can see there is a relationship between the residuals and the fitted values. There is no deviated line here. There is a proper line formed in order to tell the relationship and the linearity between residuals and fitted values. Next, let's enter again, and there is normality graph, that is the QQ plot. So there is a straight line which tells us the data is normally distributed and follow a straight line. If there has been any absence of normality, the line should have been deviated. Next graph is scale location. We can see the line is more or less straight. It is in no pattern, no deviation, and the data of residuals is spread equally along the line. There is a homoscedasticity in the data set. And the last graph, that is the residuals versus leverage or Cook's distance plot. It helps us to find out the values or observations that influence our data set. So we can see the values related to Toyota Corolla, Lincoln Continental, and Mercedes Bora. They are affecting the values of our data set. So the graph helps us to find out the observations that are influencing our model the most. So it is very easy to build a multiple linear regression model. What you have to do is you should always have a data set with proper linearity, normally distributed data, and whenever you build a model, check its accuracy and summary of the model in order to predict your values properly.